Okay, welcome. There you are. I'm Richard Shyness, and I'm the director of the summer short course. So welcome to Pittsburgh and the home of the Stanley Cup champion Pittsburgh Penguins. Forgive us if we're a little chaotic this morning. We were up last night late celebrating and watching. So there's lots of things going on in this short course, and I'm sure there's lots of different interests and lots of different knowledge bases and skills coming to the table. So let me just spend a few minutes sort of going through what we're going to do, what the goals are, and how we're going to get there. So there's many things I'd like to accomplish during this week. The first is to get you a basic knowledge of graphical causal models. The second is to get you a basic working knowledge of Tetrad 5. The third is a basic understanding of what is search and how we do it and how it works. And then the fourth is to really get you fully started on analyzing your own data and working on your own research questions with the tools that we're going to make available, and we already have made available in the center that we're all a part of as a joint effort between Carnegie Mellon and Pitt. So the way we're going to go about that is I'm going to lead the next day and a half or so in which I will basically introduce you to concepts as they come up and then move to the Tetrad program and demonstrate a certain activity in it and then turn it over to you guys to do the same thing I did and then a few more exercises so that you can actually get hands-on experience and work with the program and gain the knowledge that way. We have found that's by far the best method for doing it. So in order to actually help you, right, there's going to be, in our experience, at least, right, two spans of ability. One is people who are very comfortable with computers and very comfortable with statistical packages, et cetera, et cetera. And then there'll be those of you who are not, and I urge you to pair up into pairs so that there's one person who's comfortable and expert and one person who needs a little more help. But for those of you who don't have someone to sit next to that's going to help you, we have a bunch of Tetrad experts who are either graduate students here or faculty or whatever, and they're going to walk around and give you assistance at any time. Just raise your hand and they'll come up. So the TAs are in the back. Would the TAs just raise their hands? Raise them high. Thank you so much. And they will be here throughout the next day and a half, and then there's going to be another session on, let's see, Monday, Tuesday morning, Wednesday morning. Okay? So all the basics of causal graphical models and how to run Tetrad will be me and the TAs that have just raised their hands. And then we're going to also include in this workshop something a little different than we did last year, which are breakout sessions that will begin on Tuesday afternoon and go Tuesday afternoon, Wednesday afternoon, and Thursday afternoon. And we're going to break you out into 3 different areas and have people run those areas so that you get much more hands-on experience working with scientific data sets, real scientific problems of your own, so you can make that jump to being more fully started so you can work on your own material. So there'll also be TAs available for that, and there'll also be different rooms available. So we'll have the biggest group meet in this room, and we have 2 other rooms around, and we'll show you how that all goes. Okay, the 5th goal, I'll get back into that again in a minute. The 5th goal is really to help us make this tool and make this work more usable to anybody doing scientific work in this area. And so we really want your feedback, and we're going to collect it in various forms on how useful these sessions are to learn the basics, how useful the breakout sessions are for you to get started on your own research questions. And then when we follow up with you after the workshop, and we hope you'll respond, how useful are the tools and how useful is the support we're offering in order to actually use these tools in your own research or in the research group that you're in. Okay, so we have a person working with the center. Harry, is Harry here? Yes, Harry Hockhauser. Will you just stand up and introduce yourself for a second? This is Harry. And Harry is in charge of collecting this kind of information so that we actually have what we need to improve both these workshop sessions and the tools themselves and the support we offer with the tools so they're more useful. Okay? So that's the basic goal there. And then the sixth goal is really to help form a community of researchers, users, et cetera, all of whom are interested in causal discovery in biomedical domains and can support each other, right, in trading off best practices, questions, annoyances, et cetera. Okay? All right. So let me just go through the schedule of the workshop before I get to the content of it, all the logistics, take some questions, and then we'll dive into the actual content. So this morning, I'm going to lead until noon, and we're going to go through an introduction to the topic and then some very basic material on what we do when we represent causal systems, both qualitatively and quantitatively. And then in the afternoon, we're going to come back here. So you're on your own for lunch from 12 to 1:30. Excuse me. And then when you, am I easy to hear in the way back? Okay, so I don't have to shout. In the afternoon, every day, you should come back to this room at 1:30 to gather, and then we'll inform you on any general updates or general questions. And then in the breakout sessions, we'll break out from here, right, at 1:40 or so after we've had the updates and the questions, okay? So this afternoon, we'll just go through some material on how to estimate models, how to do inference, what model fit is, how that plays, and then we'll end the afternoon by giving you some data sets from real data, one of them uncharitable giving and maybe lead and IQ, also another case I'll show you in a few minutes, and then let you play with the program on some very simple, small cases that we all understand extremely well, at least on what the data is and what it means, and not necessarily on what is the truth, right? Different question. Dinner, you're on your own. Many great restaurants around, and it's too bad the Pirates aren't in town because they're fun to go see the baseball game. But there's a whole lot of different things in Pittsburgh. Feel free to come up to any of us and ask. Tuesday in the morning, I will jump to search, right, which is in some sense the key topic we're covering here, and go through the basics of that, and then enable you so that by the end of Tuesday morning, you can use the program to do basic search on data to look for causal models. And then in the afternoon, Tuesday, we're going to start the breakout sessions, and there are going to be 3 basic sessions, and we're going to ask you to sign up for which ones you want to go to. That sign up is not a contract, so if you decide you want to move, that's perfectly fine. But there are 3 areas, and they are brain fMRI, so we have a lot of research going on in our group and others that tries to take fMRI imaging from the brain and then figure out, using our algorithms or variants of them, what areas or what regions of the brain cause what other regions of the brain, right, in terms of processing cascade. And that's proved to be very interesting in autism research and other places, lots of exciting work, but it involves a lot of special pre-processing of the data, handling the time feature that the fMRI data presents, and lots of other really interesting features. So if you're interested in brain research using these techniques, there's going to be a breakout session for that, and that will be, I think, a lot of fun. The other 2 breakout sessions both involve similar kinds of data, but focus on different types of questions. So in the cancer breakout session, right, there's going to be data on RNA and other forms of gene expression to see which genes are going to drive cancers. And in lung disease, it's going to be similar, but there's a variety of data sets in lung disease that involve what sorts of things in signaling pathways and other places end up causing lung disease of a various sort. So the cancer and the lung disease are reasonably similar in types of the data sets, right, that they actually analyze, but they're a little different in terms of the focus and the particular algorithms and the science used. Okay, so we have here a few representatives. So who is here from the brain group? Joe, you want to raise your hand? Joe Ramsey. Joe Ramsey is the chief developer of the Tetrad program, and without whom we would be dead in the water, so be very nice to Joe. He will be your friend, And if you're mean to Joe, he will not be your friend. Very bad. And Joe has also, right, done this fantastic amount of great research in brain and fMRI. So Joe and a few other people are going to lead the brain and fMRI group. Cancer. We had a unfortunate death in the family for the person who was going to lead the cancer group. And I think, Greg, you and Jeremy are going to step. So Greg Cooper, you want to raise your hand? Greg and Jeremy Espino. Greg is the main person in the whole center, and he will speak to you on Wednesday night about the center. And then Jeremy is the lead on the systems part of our group, and he's built and will continue to build all the general tools that we're making available through the center. And so Jeremy and Greg have graciously stepped in and filled the gap there, and they're going to lead the cancer breakout session. And Takis Benos, who is the leader of our lung disease BMDP, and Takis and a few of his postdocs, TAs, are going to lead the lung disease breakout. So in the first afternoon, we'll get organized. We'll get you right using a data set that we provide, or actually using a data set that you provide, and specifying some hypotheses, right, figuring out what's what to get situated. And then we'll go farther on the next day after that. So Wednesday morning, I'll continue with the sort of the basics side of things and elevate the search instruction to include what do we do when we search for models that include hidden latent variables that you have not included in your data. Right? It's very likely that the data we measure does not include all of the causes that are operating, especially the ones that are confounders or common causes. That's important, and so we'll go over what sort of algorithms exist to do search for latent variable models as well. I'll cover some issues about measurement, which I think are very important, and I'll also leave it flexible so that any issues that sort of come up in the course of the first 2 days, I'll revisit and try to actually augment to make people understand better. And then the afternoon on Wednesday, we'll have another breakout session, and you'll do, hopefully, the meat of the research on that work. And then in the evening, we have a program at Pitt that's starting with a poster session and that has dinner. And then Greg is going to say a few words about the center in between your main course and your dessert. Okay? So Wednesday should be fun. Wednesday, usually in the afternoon, we're going to go from 1:30 to 4. But because we have this evening session on Wednesday, we will give you a little bit of a break, and we'll end at 3:30. Thursday in the morning, we're going to switch gears, and we're going to have all the data and the research area people in our center give you overviews of what they have found, right, by applying these tools to their particular research areas. So we'll have 4 half-hour talks with some Q&A, a talk on the brain, a talk on cancer, a talk on lung disease, and then a talk on, in general, more genetic regulatory network search, how it's done and what it actually has produced. And then in the afternoon, we'll conclude the breakout sessions, and then you're on your own for dinner again. And then Friday morning, we're going to have the breakout groups come report to the rest of us, both in terms of what they have experienced and found using our data sets in these areas, and what they might have found that's of interest using your own data sets that you brought. We'll have a general debrief Q&A after that, and then we'll pass out some evaluations so we can get a little bit more systematic empirical data on what we've done well and what we've done that needs improvement. Okay? And then in the afternoon, so that Friday after the morning, that concludes, right, this part of the workshop. And then we move to a second thing, which some of you are going to stay for and some of you are not, which Jeremy Espino is going to run, which is called the Datathon. Right? And there's the schedule for that. There's going to be some teams, and they're going to compete to see who can get the best scientific output in a day and a half or maybe longer. And that's going to involve, right, all sorts of sessions, and culminating with a pizza dinner from 6 to 8, as is appropriate for a hackathon, right? What? Right, Saturday there's breakfast. We're going to provide breakfast for those of you who are staying around. 10 to noon, more hacking. Lunch on your own, and then afternoon we have the more hacking, and then we have presentations at 3. Okay, let me stop and ask are there any questions?
Any of the three categories, how do we choose which one?
The way you want to choose is what type of data it is. So if it's like, if it's mRNA data or SNPs data, you want to go to one of the sessions on cancer or lung, right? If it's something involving time series, I'd go to the session on the brain. So in between now and then, come up to me or one of the session leaders and then talk to us about your data, and we'll get you placed appropriately. Okay? We'll be passing out sign-up sheets so that you guys can figure out where you might want to go, and we can figure out which rooms need the most seats, et cetera, et cetera. Okay, so that's all I'm going to say about the logistics. We'll figure out as they go. All of you should have a sheet that demarcates. Actually, let me just go back to the beginning and show you that. You should all have this sheet passed out, and let me just say a few words about that to make sure that while I'm talking about general stuff, if you need to, you can download the programs. So the Tetrad main website is on top. We have discovered, to our dismay, that the WebStart version of the program does not work properly as WebStart on Windows machines in every case. So we've created two versions of the download. The difference is reasonably simple to describe. So the JNLP version, right, is a WebStart-enabled system whereby when you first download it, it deposits an executable jar in Java on your machine, and thereafter, when you double-click on that icon on your desktop, the program checks to see, first, if it has an internet connection, and if so, it goes to Tetrad's site and asks, is there a more recent version, right, that has been produced, right, when we discover a bug or two that we always discover. And if so, it downloads the most recent version automatically without you doing anything and opens that up when you actually get the program to open. And if you're not internet connected, so if you're offline, right, it just opens up the version you have on your machine, right, that's most recent. If that doesn't work, right, which doesn't work on my machine, then we have this other version that's a jar file, which is simply an executable that runs if you have Java installed on your machine. So the website is pretty clear that you need Java, and if you don't have Java, it shows you how to get it. Lizzie.
Is there anyone who can't get on the Wi-Fi? Ends up.
Oh, okay, so yeah, there's a, I forgot about that. There's a Wi-Fi thing, and you should all have access, but if you don't, raise your hand. Okay, so most people are getting on it. And then the file at the bottom, right, which is the place where we're storing data sets for you guys to use, and we'll also give you the slide presentations I'm having, right, should be available there. Joe, have you populated that with the slides that I gave you?
I have.
You have. Okay, so for any of you who want to follow along with my slides, right, they should be available in that data files, and also some of the actual files that we're going to have you download and work with will be available there. And so that should be, you should have that as a physical sheet that we can give you if you don't want to, yeah.
You said that the file was for your lecture ones?
Yes.
Because right now there's just like text files, maybe I'm misunderstanding.
Go up a level into the 2016, and that's where the data sets,
Right in front of me.
got it? That's all right. Everybody has one of these sheets, and they should be available outside if not. Excuse me. Okay, so on to the content of the workshop. So I'm going to give you one slide on the history of causal graphical models. It's admittedly very biased and self-serving, such as life. It gives you a simple perspective, I think, that's helpful. Right? So in some sense, all of this work dates back to Francis Bacon and Galileo. Bacon was the first one to really articulate in any systematic way methods one could take scientifically, right, to observe regularities in the world, and then from that, right, make inferences about what we might care about, which is causal claims. Right? And he did it long before John Stuart Mill, and I think in some sense he did it quite a lot better. So if you are curious about the real foundations methodologically, right, you might go read Francis Bacon. A lot of fun. And Galileo and the end of the 16th and the beginning of the 17th century really forged the way for everybody ahead for how to do a completely controlled experiment, in which case you have lots of different factors you control perfectly, and then you can observe and measure an output, and then you take one of those factors and wiggle it systematically while you keep the others fixed, right? And then figure out what causes what with that controlled experimental regime. The biggest extension, I think, on experimentation as it affects causal inference next really comes from Ronald Fisher. So Ronald Fisher, in the early part of the 20th century, he did this magnificent extension of Galileo's paradigm, in which, as opposed to being able to control every factor, right, as long as you could randomly, right, assign one of the factors and let all the other factors distribute, right, as they will, then at least probabilistically and statistically, you could accomplish the same thing that Galileo has accomplished, but then have to make statistical inferences about whether or not you were being effective. So Fisher was this enormous giant. But before Fisher, there were a couple of people who were quite explicit about the intent of the science being causal and not just statistical, right? So it's really become very, very fashionable of late to talk about causation explicitly, but for a long time, I think in the 70s, 80s, 90s, right, nobody would use the word causation. It was considered sort of taboo. People would say there's a statistical link or there's some other link, but they wouldn't use the word cause. Udny Yule, right, was the first guy that I know about to really explicitly go after causal questions using regression and techniques like that. And he looked in England about questions about whether or not, right, putting people on some type of welfare back then led to them becoming dependent on the government, right, or becoming more self-reliant and getting back on their feet. So Udny Yule was an early progenitor of explicit causal goals. Charles Spearman, right, was the first guy to really take seriously using statistical sorts of evidence to get at hidden variables that we can't observe directly. So Spearman was the guy who came up with this G, right, that stands for general intelligence, if those of you have heard of that. And what he argued, very, very interestingly, was that if you gave people multiple tests in math and reading, and you looked at the correlations between those tests, that there was a pattern of constraint that you could observe in those correlations that would confirm that there was this single factor G called general intelligence. And that constraint was a Tetrad equation, right, which is the motivating name for the project that I've been involved in for many, many years. And it essentially said if you have four variables, right, and the product of two correlations permuted all three ways, right, are all equal, then you have a Tetrad constraint, which you can test in the data and which will confirm that you have something unobserved that behaves in a certain way and causes those tests in a certain way. So Fisher, although he was in some sense quite primitive and wrong in lots of ways, right, he was really a pioneer in trying to connect something interesting about hidden variables to observable things we could test in the data. Right? So the connection between causal structure and testable constraints really goes back to Charles Spearman. Sewell Wright, on the top there, was in biology and genetics, and he was the first guy to really take seriously the idea that if I built you an arrow diagram, right, then it's not just a qualitative object. This could actually connect to real predictions that I could test as a function of the graph, and then I could use the graph as a shortcut to compute, right, what the different mechanisms by which genes or other things led to phenotypes or observable things, and how those different mechanisms compare to each other in terms of weight. So Sewell Wright was the first really to build path diagrams, which then became the precursor of, right, causal graphs interpreted statistically. Fisher, you know. On the bottom in 1930, I have Jerzy Neyman, and he's important because he was also extremely clear and careful about formalizing an idea of what we're doing when we take data and we try to understand what's causing what. Right? So he started what's really now known as the potential outcomes framework, in which the idea is essentially if I give somebody treatment and I give somebody control in a biomedical sort of context, right? So suppose I give you treatment, right, and I give Takas control. I don't get to observe what you would have done if you had been given treatment, and I don't get to observe what Takas would have responded like if he had been given the control. So it's an unobserved, unmeasured, right, missing data problem, as it were, and what we really care about is the potential of what would have happened had we given different treatments than we did. So he formalized that idea to make it clear, and that's been actually taken and made very, very rich now as a formalism that one can use called the potential outcomes framework. And it's been made famous by Don Rubin and many other people, and it's used very, very widely in epidemiology, biology, all sorts of different things. Jamie Robbins and a group that was here in philosophy, and Greg Cooper and many others in Europe, right, took some of the ideas from Sewell Wright and from other people and converted them into and Judea Pearl was a giant in this field, converted them into a formal structure that's now known as causal graphical models, and that's the framework that we'll be going over and working with this week. And the reason is very clear that potential outcomes are very, very powerful and useful if one is pretty confident and knows a lot about the underlying model, and there's a parameter or two one wants to estimate. If you don't have a lot of confidence about the underlying model and you need to find it out, then graphical models allow you to search, and right, that invokes all the stuff we do, and so it's a whole different competing way. There's no competition in some underlying sense. You can translate one to the other, and so it really reduces to what's more convenient cognitively, what's more convenient psychologically, what's more convenient computationally. Okay, so I think now we've come to this wonderful time in history in which we really have a very rich theory of what I call statistical causal models. And I put the word statistical in green to represent the sort of everything's okay, we can get data and we can do our normal statistics on it, right? And I put the word causal in red because now you're crossing a bridge and you're entering dangerous territory where you're making claims that are a little bit bigger than just there's a correlation or there's an association or there's something statistical that we can describe about the data. Okay, so but we have this modern theory of statistical causal models, and graphical models are a part of it. Theories about intervention and manipulation are a part of that. They're very important. And potential outcome models connect to that in an important way. Counterfactuals, what would have happened if we had done something differently than we did, can be formalized and made very interesting in this framework. And then we have this connection between causal models and testable constraints that allow us to get access to whether or not our causal models are accurate according to the predictions they make in the data that we can test, right? So if I say to you, X causes Y, what could you test about that? And you say, well, you could test whether they're correlated or not. That's true, right? If X doesn't cause Y, right, it might not be the case that they're correlated, but it might also be the case that they're correlated if there's some common cause of them and there's some other way they're arranged so that Y causes X. So the general project of connecting testable constraints to the structure of a causal model is where we're focused, right, in Carnegie Mellon in this center. Okay, so the first thing I want to say is that you have to have your head around this inequality in a really, really firm way to even begin this sort of field. And the idea then, if you're going to predict, right, what's going to happen, and you've observed, right, that's a little different than predicting what's going to happen if you intervene, right? So predicting after an observation is not the same as predicting after an intervention. And getting that clear, right, is one of the key ideas behind this whole field. So here's an example that should make it vivid, right? This statement is a conditional probability that says the probability that an individual will have lung cancer in 1960, that's equal yes, conditional given that your tar-stained fingers in 1950 are equal to no. That means your hand or your fingers do not have any tar stains on them, right? Who knows what that number is, but right, we could say we might be able to actually estimate that from data. But the key thing is that's not the same as the same apparent conditional probability, where instead of conditioning on the observation that someone has clean fingers, we're now going to condition on an intervention in which we set their fingers to be clean. How might we do that? We might give them soap with nicotine solvent or tar stain solvent soap, and then say, go in the bathroom, wash your hands for 20 minutes, right? Come out, and then we say, okay, now what's the probability that that person, right, has lung cancer 10 years later, given that we've set their fingers to clean, right? Well, if we've made them wash their hands and set their fingers to clean, right, any information we might have gotten from their fingers, right, is lost, because fingers don't actually cause lung cancer. They're just an indicator of whether you smoke or not, and smoking is what causes lung cancer, okay? So these probabilities are not the same. And that's the problem with causal inference, right? If they were the same, this would all be pretty easy. We just, collect information, do conditional distributions, all is good. And in the field of machine learning, in some large way, right, this problem is, right, completely endemic, because we've gotten extremely good in machine learning at building predictions, right, about one thing from a whole bunch of data about another. But that doesn't mean that we're any better at getting to the causal question of what would happen if we had intervened. So those are the big things. So in general, conditional probabilities are not the same as conditional and intervention probabilities. If they were, it'd be easy. And when we do causal versus statistical prediction, in the way I think of it at least, right, we're starting out in many cases with data that's non-experimental. So I haven't done a biomedical trial, or I haven't done some kind of an experiment. I've just collected data, right? and then from background knowledge and that data, I might be able to do some inference or estimation about, well, what's the probability distribution that would govern, right, the variables that I've collected data on in the population. So there's some population out there. I've sampled data, and I've gotten the background data, and I've gotten that data, and with background knowledge about assumptions, I can do an estimate of what is the probability distribution that I was drawing data from. And then if I have that, I can also then estimate any of the conditional distributions, right? So I can estimate what's the probability that y would equal some value given I've observed x to equal some value and z to equal some value. So this is what I think people do typically in statistical inference, statistical estimation contexts, when they're trying to predict y in a non-causal context. But if you want to actually make a causal prediction, you need to know something about the causal structure, and then from the distribution that you might have estimated and the causal structure, you can then estimate the probability of some variable given you've done something to at least some of the variables that might influence that variable y. So you can't do this unless you have this. There's just no way around it. So in some sense, causal prediction is really strictly harder than statistical prediction. Okay, any questions so far? Is all reasonably clear? Okay, and the final thing I want to say before we get into the, the details is to, again, motivate the idea of, in some contexts, you're doing estimation, and in some contexts, you're doing search, and they're different activities. So here's an example of what you might consider estimation and when potential outcomes might be used. So the causal question was, what's the effect of this drug, zidovudine, on survival among HIV-positive men? This is an article by Miguel Hernan in 2000, beautiful article. The problem was that there's confounders, right, your CD4 lymphocyte count, that vary over time and that are dependent on the previous treatment you got of zidovudine, because these are sequential treatments in which we give somebody a dosage at the beginning of a trial, and then later on we monitor how they're doing, and then we change the dosage one way or the other. So there's a sequence of interventions, and estimating the effect of a particular sequence of interventions on the actual response is very complicated, and partly because, right? There are these confounders that actually vary over time. So Hernan and a few others came up with this beautiful application of this technique called marginal structural models, and they estimated the effect, and they assumed that the treatment was measured reliably, so we actually had a good set of data about who got what treatment. And we measured the covariates, and those were sufficient to capture the major sources of confounding, so we didn't have any big confounders we left out. And then the model of the treatment given in the past is accurate. So if all those assumptions are correct, then we had an output that's the effect estimate with confidence intervals around how big or small we thought that might be given the random chance in the data. So the fundamental problem is that any of the estimation that we're doing here and any of the inference about the confidence intervals is entirely conditional on the model. And I'll get to that in a whole bunch of different ways as we go on, but this is a crucial idea. So you've all seen, right, hypothesis tests, confidence intervals, et cetera, p-value of above 0.05 or below 0.05. All of those quantities that look very precise and very, very scientific are all dependent upon the other pieces of the model being specified correctly, all the assumptions being made accurately, right, the other numbers that you're actually using being accurate, et cetera. So all that estimation is conditional on the model, and it's very rare that that dependence on the rest of the model is actually specified and put formally in any explicit way. So if you're really a Bayesian, right, and you do things honestly, and you say, I'm uncertain about all these different pieces of the model, right, and all that uncertainty is going to ramify out into my uncertainty about a particular parameter estimate, then you might get a better and more accurate confidence interval or estimate, but you'll be so depressed that you won't be able to carry on. Because the uncertainty is so big, usually in these models, that by the time you ramify it out to the parameter you care about, the possible values are ranging from, negative a billion to a positive a billion, where what you really care about is a 5 unit difference. So I think people, for good reasons of mental health, tend not to be honest in that way. And it's also computationally quite difficult. So we usually tend to ignore the uncertainties in the rest of the model. Okay, here's another context in which search was the appropriate technique, and actually, if time permits and you want, I can show you a little bit more about this case. But there's this plant called Arabidopsis, and a set of colleagues we have in Zurich wondered about which genes in Arabidopsis actually affected flowering time, because flowering time turns out to be very important in the business of growing these flowers, because if you know how long they take to flower, then you can go to market at the right time, et cetera, et cetera. Problem is there were 25,000 potential genes which might actually affect flowering time, and they didn't really know ahead of time a lot about which genes were going to affect flowering time or not. Well, that's a huge search space, and if I said to you, right, go to it, and matter of fact, suppose I said to you, you're in charge, and you get to use all of us as, right, workers, and assign to us each to do some experiment where we actually get to knock out one of these genes or do upregulation of one of these genes and then see if flowering happens, right? How long do you think it would take you to figure out which of these 25,000 genes were actually causing flowering? A really long time, right? So that strategy, even if she had that kind of power, right, and you were all willing to work for her, right, it would not be nearly quick enough to actually get through 25,000 genes in any feasible sense. So instead of just trying all those experiments, the idea was, let's do some search and narrow the field down to a set of candidate genes, right, from the techniques that we've developed and others have developed, and then use experiments to confirm which of those candidates seem to actually affect flowering time. So that's what was done. So the assumptions were that the RNA microarray measurements, right, that they were taking were a reasonable proxy for gene expression levels, right? And assumptions I'll get to about the causal Markov assumption later, et cetera, and many others. And then the output was, right, a set of possible candidates, a set of possible models, which then could be used, right, as follow-up experiments. So the results here were very interesting. They came up with about 25 suggestions. Of those 25, they could actually test 13 of them. They had right, seeds available that would actually test those 13, and of those 13, about 9, right, produced viable plants, and of the 9, I think 4 or 5, right, successfully actually controlled flowering time. So compared to the base rate of 25,000, right, this was an incredible victory. We hoped we could, do as well or better, but you can see the idea here. It's a really, really effective method if you're very uncertain about the structure going on or about the which subset of a huge number of possible genes are actually making a difference. And the fundamental problem with this is that the number of models, right, the number of causal structures, grows super exponentially with the number of variables. So the number of causal structures that I could write down with 2 or 3 variables is manageable. Once I get to 7, 8, 9, 10, forget about it. And once I get to 100, if you don't have a good algorithm to search the computer, forget about it as well, right? So you really need to be very, very careful about how you search the space, because it grows so quickly, so big, that anything that's not efficient and well done, you can just forget. It'll take forever. So that's the problem in this space. Okay. So in causal search, the real idea is not to find a single causal model. Well, that would be nice in some cases. It's to find all the models that really are indistinguishable, given what we think we know in background knowledge and the data, right? So in some cases, right, that's still a pretty large set, and there's just nothing to be done about that if we don't know a lot, and the data is just in a place where it doesn't tell us a lot about what's causing what behind the scenes. But we still want to be able to represent, right, features causally that are common to all the models that we can't distinguish between. So this is a big deal for us. We really take seriously the idea that you're not trying to find a particular model, you're just trying to find anything that the data will tell you, but no more. So that's actually pretty complicated. Now, it turns out that the usual tool that people use for non-experimental data, it's still completely ubiquitous in the field, is multiple regression. How many of you have actually learned multiple regression in one place or another? Yeah, so a large number of you, right? It turns out multiple regression is really, in many cases, if not most, the wrong tool for causal discovery, right? And I'm going to give you a very concrete example of it right now. And it's foreign investment in democracy. So this is an example taken from way back in the 1980s when there was still a hot and heavy debate about whether or not investing, right, in third world countries, right, would produce, right, foreign investment would produce a bad situation in which those countries would become more autocratic, more dependent upon first world investment, right, and then less responsive to the needs of their people. That was dependency theory. Or whether foreign investment would be a good thing because it would actually improve the economic situation, it would help economic development, which in turn would lead to less autocratic, more representative political regimes. So this was a hot and heavy debate, and these guys, Timberlake and Williams, did a study in which they tried to collect data and answer this question in one way or the other. And so the title of their paper was Dependence, Political Exclusion, and Government Repression. So they measured 4 variables, or the Handbook of Political Indicators included these 4 variables, and they got measures of them on 72 countries that included, right, neither the US nor Russia at that point, Soviet Union at that point, nor China or any of the other special weird big ones. And these variables included political exclusion, right? How much did these countries exclude the population from being represented in the political process, right? Now, you may argue that our country is not quite as democratic as it should be, right? But on most measures, right, you're allowed to vote, et cetera, et cetera. So we're pretty low on PO, and many other countries are pretty high. Civil liberties, like what do you allow the population in terms of freedom of press, freedom of assembly, et cetera, et cetera. And then energy consumption per capita, which is the totally standard measure of the level of economic development. So it's the log of energy consumption per capita that's taken to be a measure of how economically developed a country is. And then this is the big key one, which is foreign investment, how many dollars are flowing from foreign countries into a third world country. Here are the correlations that were measured among these variables, and the key one is right there. And to get your head around this, since political exclusion, PO, the higher PO is, the more exclusive, right? What does this correlation say about the prima facie relationship between foreign investment and political exclusion? Yeah. Political exclusion. Exactly. So more investment goes with less exclusion. So it sounds like on the prima facie case that foreign investment is a good thing. It reduces political exclusion, if it's causal, right? Exactly. So they did a regression in order to control for other potential confounders, which were energy level, economic development, and civil liberties. And here's what they got. So you can see the key coefficient, right, when we're looking at how political exclusion depends on foreign investment, even though the correlation was negative, now the regression coefficient is positive. So the sign has flipped. So their argument is essentially that, well, it may be that foreign investment is negatively correlated with political exclusion, but when we control for these other factors, we can reveal the causal influence, and it turns out to be positive, which means that more foreign investment causes more political exclusion. This was a dependency theory gem. They really loved this result. And you can see the statistics, right? The standard error for that coefficient is 0.05, the t is 3.9, and so the p-value is very low, and that means that coefficient is highly significant, which of course they pointed out in the paper at least 6 times. All right. So the interpretation was, yeah, foreign investment increases political repression, and we should leave these countries alone and stop investing. Okay, so here's a graphical interpretation of that model. Right? So it makes these black lines that have no arrows on them really represent, we don't have any idea what's going on. These variables are just freely correlated. We don't care how they're related. So this is sort of a mixed causal graph. But the other features of the graph are arrows that point from these various measured factors to the key outcome, which is political exclusion. And the key one right there is 0.217, which represents the influence of foreign investment on political exclusion as positive. All right. How, if I were asking you to review this paper, those of you who have actually done any of this kind of research, what would you look for to say, yeah, this is a reasonable model statistically? So we all agree it might make some sense, maybe. But what about, what would I look for statistically that would tell me that's a good model and I should trust it? Yeah?
Just having another test case or another two-dimensional benchmark that whether it's good or not, so like know the outcomes, basically.
Suppose all you had was this data set. That's it. And how does this model, right, and the data set, what could it say that would tell you that this is a good model? Yeah.
Testing against alternative models, which there are different pathway or different relationship between the three predictors.
Good. Okay, so I'll get to that in a second. So, right, if there are alternative models, right, that also, in some sense, fit the data or explain the data equally well, we ought to know about them. Right? That's your basic point? Yeah. Okay. Yeah.
Permutation analysis kind of random assemble some variables and see if you see the similar pattern.
You mean permute the data or do bootstrap on the data? You could do that, but that's just another form of giving you statistical inference about what variability we might see in the estimates given that we know the variability that we could expect in the data. So that doesn't really get to the actual model. Well, I'll give you what I take to be pretty standard is people will report the R squared, which is how much of the variation in the outcome, PO, is explained, right, by variation in the inputs. Now, that will give you some idea, right, of the statistical association between those three on the top and PO on the bottom, but it has nothing to do with whether this structure causally is the true structure. And I'm saying nothing to do, almost, okay? So there is actually no constraint on the data that a regression model like this entails that allows us to test the causal structure of the model. And that's the sad part. There is a regression, right, is in this kind of a form a completely under-constrained model which will fit any data, right? So there is no degrees of freedom. There are no constraints. Regression models are completely untestable in a certain way, except for the other parts of them that involve the assumptions about normality, the assumptions about uncorrelated error, et cetera. So they're diagnoses, but they're not to do with this causal structure. They're to deal with other features of this model. But let's go to that gentleman's suggestion about other possible models. We ran this same data through Tetrad and the PC algorithm. This is what we got. Now, without explaining that too heavily, right, this double-headed arrow represents the fact that either there's some hidden latent variable that's underneath the scenes we didn't measure, right, or there's some other causal arrangement that we can't model with just these variables, right? This represents the idea that, well, whatever the relationship is between political exclusion and civil liberties, it doesn't look like civil liberties cause political exclusion. If anything, it's the other way, but which actually kind of makes sense, right? If you're in a politically exclusive regime, you'll probably be more free and you'll feel more free to reduce civil liberties, right? If you're going to be reelected or go up for reelection, you probably want to do more to produce civil liberties. And what it says about foreign investment is that it's strictly a sink. It doesn't cause anything. It's only a response, right, to the economic development, right, and maybe it's related to the civil liberties. So it completely contradicts the causal structure that we're seeing. And here's another output for Tetrad that involves the possibility of latent variables, and I'll get all back to that in day 2. But when we actually parameterize this model and then estimated it using the same assumptions as a regression, this model does entail 2 constraints that we can test in the data. These are predictions that we can test just from the causal structure. And it turns out, and I'll also go into more of this afternoon, it turns out that this model fits the data extremely well. And what it says, right, is that, right, even if we're generous about the causal structure here, that economic development, right, reduces political exclusion, which sort of makes sense. And it says that economic development is what positively causes foreign investment, which also a little bit makes sense, right? And it says that political exclusion, right, causes lack, and CV is also the lack of. So the lack of political inclusivity causes the lack of civil liberties, right? All very plausible. Fits the model. And it turns out even further that there is no model with testable constraints that fits this data that's not rejected. I'm sorry, there is no testable model in which foreign investment is a cause of PO and has a positive. There is no model of any sort that you can actually test. So this is a clear example, I think, where using multiple regression has just failed us and we need more sophisticated tools. All right, that's kind of a complicated around the, but everybody get that? It's kind of a cool example because it's so simple. Okay, I'm now going to switch gears and go into the positive theory of causal graphical models. Everybody good? All right. Causal graphs. So the first thing to really get at in all this is the idea of a representation for a causal system that's entirely qualitative. There are no numbers involved. There are no probabilities. There are no numbers of any type. It's simply a yes or no, right? The causal relationship exists or it doesn't. And causal graphs are the simplest thing, and every, right, causal graph, involves a set of variables which we box and a set of arrows that are called directed edges or edges that connect those boxes. And an arrow means that the head of the arrow, or the tail, I can never remember that, the cause, right, is a direct cause of the effect relative to the other variables in the system. So here I say years of education is a cause of income. I don't think anybody would dispute that, right? It's a direct cause of income in that graph. It's not a direct cause in the graph below because now I've included another variable, which is any of the skills or any of the knowledge, including networking among people you might actually get employed by later, right? So if you're going to get anything relevant to income from education, it's going to be because you learn some skills, you learn some knowledge, you make some networking contacts, etc. Right? So once I have this, right, this is no longer a direct cause of income. So the idea of direct cause has nothing absolute about it. It's entirely relative to what variables I articulate and put in the model. Okay. Now, you know that there's many other factors that influence some of these variables that I have not put in this particular graph. Does that make the graph useless or incorrect or obsolete? No. Right? It's perfectly okay for me to leave out all sorts of other causes of income. I might be born into the right family, I might be born into the right town, I might be born into the right time. There's lots of other factors besides what I can do and what I know that affect my income. That's the way the world happens to be. So there's nothing wrong about writing down a causal graph and claiming it's accurate and true, even though you've omitted causes of all the variables in that graph. On the other hand, you are making a claim that the graph is common cause complete. So I can't have an omitted common cause and then say the graph is accurate. So that's not allowed. Right? So this is not a claim about what's true and what's not. It's a claim about what you mean when you claim a causal graph accurately represents the world. You don't mean that it's including all the causes. You do mean that it's including all the common causes. And that's a little subtle and it's a little bit difficult. We can go back over that if you like. Okay, so now, just to get you started on Tetrad, we're going to move into, right, actually having you use the program. And I'm going to demonstrate what I want you to do, right, and then I'll turn it over to you guys so you're making sure you're into that thing. Okay, so when you load the program, what you'll see is this workbench. Oh, you don't see it. There we go. Forgive me, I'm going to have to stand backwards here because I can't see it on my own screen. Okay, so you see the program, and it's got a big workbench, and on the left it has all these different buttons and tools that we can then click on and deposit onto the workbench and work with. So the first one on the very top underneath the general selection tool is called Graph. So if I click on that, the cursor changes. I left click where I want to put a graph. I can do more than one. And they all come up on the workbench as gray objects, which connotes they're there, but there's nothing in them. So to put something in them, I double click on that object, and then I'm given this pull down that's a choice about what kind of a graph to use. Directed acyclic graph is one of them. Structural equation model, general graph. Choose directed acyclic graph. And once you choose it once, when you open a new graph after that, your default will be directed acyclic graphs. You only should have to do this choice once. You say OK, and then this gives you a choice of whether you want to do everything manually or whether you want to have the program automatically build you something that you can then work with in some future. So say an empty graph to be constructed manually, and say OK. And now you're put into what's called the graph editor. Right? So this is the basic tool for building a causal graph that represents something you might want to actually study. So to put a variable on this graph, you can either put a boxed variable or a circled variable. The boxed variables are taken to be measured variables. Data will come out. And the circles are latent variables. Data will not. There's no difference in the way they act behind the scenes. The only difference is whether you'll see data about them. Okay? So I'm going to do all measured variables. I just click on them where I want them. And then to rename them, I can just double click on them. And then I'm put in this little dialog box, and I can type in something like smokes. and that renames it, and then I can do this as YF for yellow fingers, and then this LC for lung cancer. So then I have my variables and I've named them. And then to actually put the causal relationships in play, I go to the left and I click on this arrow tool, and then I click on the cause, hold the left button down, drag it, let go when it reaches the effect, and the cause will be deposited for me. And if I want to move these variables around so the display looks pretty, I click on this hand tool, and then I go grab the variable, move it around, and the arrows follow. Wonderful. Okay? So that's all it takes to build a causal graph. And when I say save, you can see that that graph has now been called a DAG, directed acyclic graph. This is, right, still empty, and that's to tell you what's in what. If I want to actually destroy something so it's emptied and I can redeposit contents in it, I right-click on it, and there's lots of different options. I can destroy the model. I can rename the box. I can delete the box. I can do all sorts of things. So if you're ever in confusion or doubt, you might right-click an object, and options will appear that Joe Ramsey has ingeniously invented. But in this case, I've just built a simple graph, so when I click on it twice, it pops up, and there it is. Okay? So you guys now go ahead and build this graph, and then build a second graph, right, in this space, which has any variables that you think of that are interesting to you, and maybe use 4 variables instead of 3. Okay? So that'll just give you the minimal facility with loading the program and actually building a causal graph. So go ahead and do that. We'll walk around and help, and then we'll take a 10-minute break when you have finished at about 10:15.